Okay, so last part of the Bayesian estimation is the Bayesian testing procedure. So this is a very simple testing procedure, as you will see, but there are different approaches actually in this field. So you know, Bayesian estimation or Bayesian theory is deep topic actually, so you have to go deeper, and it has lots of applications in many fields. I know, for example, for time series analysis, there are specific books for Bayesian time series analysis, and it's hard actually. So the theory behind it, and also the computationally. So you have to use. Usually, if you are using Bayesian approach, usually you have to deal with the computational stuff a lot. So usually we don't end up with the exact results or closed form solutions, so we have to use some kind of computational approaches to get estimates, and usually we use iterative methods to solve the problems. So we are talking about very simple parts right now. Okay, so Bayesian testing procedure. Okay, so again we have a random variable x. We know it's PDF or PMF. Okay, so this is known. Theta is in the parameter space, and our aim is to be able to estimate that. And let's consider the hypothesis where theta is in the null space versus alternative theta is in the alternative space. And we know the prior distribution, so the procedure is the same. Prior distribution of theta, and then we are taking our sample and combine prior and sample information to get the posterior distribution. Okay, so this part is the same, posterior distribution of theta. Okay, so basically we have two different areas for theta in the hypothesis testing part, where theta is in the null space and alternative space. So we have to consider the probability. So in usually Bayesian approach, we usually work with the probabilities, and the results are based on probabilities. And if the probability is high, then we assume that the highest probability will be in the reality. We will have that highest probability case. So we use this simple approach in the hypothesis testing. So we are using the posterior distribution for the parameter of theta to compute the following conditional probabilities. Okay, so probability that theta is in the null space given the sample information, and we are finding the probability that theta is in the alternative space. And we have a very simple procedure. So if the null hypothesis is true, then the probability of this part will be higher. If null hypothesis is not correct, then the probability of this part will be higher. So it's very simple. So we have to just check which probability is higher than the other case. Okay. So in the Bayesian approach or Bayesian framework, let's say, these conditions or conditional probabilities actually represents the truth of H0 and H1 respectively. Okay, a simple rule is to accept H0 if the probability of theta in the null space is higher than the probability that theta is in the alternative space. Okay, so this is xn. Otherwise, accept h1. Okay, so it's just that simple. So let's consider an example. Let's say we have a Poisson distributed random variable, and the theta prior is given as gamma, alpha, and beta. Here we assume that alpha and beta are known because this is the prior information. This alpha and beta should be known. So let's say we have a random sample. Okay, then our hypothesis is this one: theta less than or equal to 10 versus theta greater than 10. Okay. Okay, so first of all, we need to define some case here about theta. But we don't have to deal with that actually, I think. Okay, then calculate first posterior distribution. Okay. It's proportional to the likelihood and multiplication with the prior. So we have a gamma, Poisson random variable, and we have a gamma PDF. Okay, so here theta is the main thing here. So get rid of the other things other than theta. So combine each value with theta. So we have theta to the summation xi plus alpha minus 1 and e to the minus theta. And we have n plus 1 over beta. Again, from here we need to understand how here also we know that the range of theta is positive. Okay, you know. So it's a continuous random variable. So it has a continuous distribution here. Okay, so you have to be careful about that part. So again, you have to recognize the distribution by just looking at the form of this shape. Okay, again, we have a random variable to the parameter minus 1 and e to the minus parameter times, random variable times a parameter. So it's the form of gamma distribution, right? Without calculating the denominator, we can get that our alpha is now this, and our beta is now m plus beta. Okay, I just write it this way. Then we can say that the posterior PDF is gamma. And the beta scale parameter as this one. Okay, then our decision rule. Except H0 F. So we have to consider the probability that we have 0 to 10. Okay, then we have the gamma case, alpha plus summation xi, and we have this alpha plus summation xi term, theta to the summation xi plus alpha minus 1 and e to the minus n beta term. Okay, the theta. So if this is greater than or equal to, so I will write this part, from 10 to infinity. Okay, the same thing actually, we have to write the same thing here. Okay. Let's see. Okay, so this part will be reversed. Oh, that part is correct, sorry. Okay. So this part should be -1, okay, and plus beta d theta, okay. So these are constants, okay, so this part and this part goes, and then what we have here is except H0 if, so we have to calculate this actually from 0 to 10, so theta 0. Actually, we can say theta, but to make sure that we have different values, or let me write it as theta, because the regions are different. D theta, and the same thing from 0 to infinity. Okay, so there's a minus sign here, d theta. So this is our decision rule. Okay, so after taking a sample, we can get some information. Let's use some data here. So 11, 7, 11, 6, 5, 9, 14, 10, 9, and 5, 8, 10, 8, 10, 12, 9, 3, 12, 14, and 4. Okay, so n equals to 20 here. And since we said that, so let's see, we have a Poisson and a variable. Okay, so we have a gamma distribution under H0. Prior distribution for gamma will be 10, and theta is 10 here. Okay, so let me, well, so we are talking about Poisson. Why did I write Poisson 8? So this is a different thing, sorry about that. So I need to erase these. Okay, so n is this one, and here we have Poisson. We are testing that our theta is 10, right? Okay, so we have this prior information also. Suppose we think theta is about 12, but we are not quite sure about that. Hence, we choose the prior distribution for gamma distribution like that, then the mean of the prior will be 12. Okay, so we have this prior information, let's say, and based on that And based on that, we can calculate the summation of xi, which is 177. So this is actually the sufficient statistic for theta in the classical approach, Then the theta posterior will be gamma, and we have this plus alpha, and okay, and this gives us gamma 187 and 0.048. Okay, then using this Bayes estimate under the squared error loss function as the mean, which is 8.976 under squared error loss function. Okay, then when we calculate theta less than or equal to 10, given that the summation xi equals to 177, is calculated as you can use chi-square tables to be able to get that. This one, okay, or you can just use R or even Excel to be able to get that. And the reverse probability, you don't have to calculate that, just subtract the previous value from 1. You don't have to calculate actually, but let's find it. So this means that probability that theta, this quantity under the null hypothesis, is greater than, maybe don't put an equality here, greater than probability that theta greater than 10 given summation xi. Okay, so this means that we need to accept H0. Okay, then after that we can also find the 95% credible interval. Again, we set our alpha as 0.05 here for theta as 7.77 and 10.31. And as you can see, actually this contains 10. So actually this also says that we cannot reject the null hypothesis. Okay, so this is a very simple example, and this is the end of the Bayesian estimation part, and also end of all our course actually. So we have to cover, we covered all the topics that we have to cover. So thank you very much for following the courses and joining the meeting hours also. I hope I can see you soon. Take care. We will meet tomorrow, Wednesday at 11 a.m. Okay, take care. Bye bye.